In this video, I will show you how to simplify expressions involving imaginary numbers. Now, we know that if we take the square root of a perfect square like 9, for example, the square root of 9 is 3. On the other hand, the square root of negative 9, we can't take the square root of negative 9 because, 3 times 3 is 9, but there's nothing times itself that's going to equal negative 9. So we have to use this concept of an imaginary number. I is defined as the square root of negative 1. And so using that concept, I can, whenever I see a negative under the radical, I know that that is going to be this I, this imaginary unit. So this is immediately going to become I times the square root of 9. And then I can go ahead and do it. The square root of 9 is 3, so this will be 3I. And by the way, the I goes after the 3. So that's the basic idea. Now, with that in mind, I'm going to show you two ways to do problems like number 1. So first of all, as soon as I see that negative sign, I know that there's going to be an I involved. Alright, so forget the negative sign. We already know that's going to be I. That leaves us dealing with what is the square root of 48. Now, when the numbers are small like this, we can usually just use our multiplication facts. For example, see, I'm trying to think of a perfect square that divides evenly into 48. And if I'm lucky, I remember that 48 is 16 times 3. The square root of 16 is 4. So that would make this 4 radical 3. So that means the answer would be 4I radical 3. Notice when I have a regular number and a square root, the I goes in the middle. Now, many of you might not have known that 48 was 16 times 3. So you would certainly know that 4 goes evenly into 48. So you might have done this, and you might have said, okay, 4 goes into 48 12 times. 4 times 12 is 48. And then you would have said the square root of 4 is 2, so this would have been 2 radical 12. Obviously, that's not the same as 4 radical 3 because this is not completely simplified yet. Looking at the 12, if we try to simplify this further, again looking for a perfect square that divides evenly, 4 goes into 12 again. 4 times 3. Now, I've still got this 2 in the front. I'm just going to bring that down. The square root of 4 is 2, so then I have 2 radical 3. I'm going to bring down this 2. This is multiplication that's happening here. All of this is multiplication. So that's why I get 4 radical 3, which is the same thing I had before. Okay, so that's one way to do it, is using our multiplication facts and just breaking it down step by step. Now, here's another way that you can do it. It's called prime factorization. This is very useful when the numbers get bigger, like 384, things like that, even bigger. Remember factor trees? You can sit here and say what times what makes 48. And you can pick anything you want. It doesn't have to be perfect squares. When I look at 48, the first thing that pops into my head is 6 times 8. 6 times 8 is 48. Both of these can factor further. 6 is 2 times 3. These are both prime numbers, so I'm going to go ahead and circle those. That's the end of those branches. 8 is 2 times 4. Okay, 2 is a prime number. And then 4 is 2 times 2. Prime numbers. Okay, so the prime factorization. I have, let's see, 1, 2, 3, 4 2's. So 48 is the same thing as 2 times 2 times 2 times 2. and then times 3. That's what we're dealing with. Now, every pair of these is a perfect square, because 2 times 2 is 4, and the square root of 4 is 2. So this pair will become 2 on the outside of the radical. The same thing with this pair, or this pair of 2's will turn out to be a regular 2 outside the radical. Again, because this is really 4, and the square root of 4 is 2. And then 3 is the only one that doesn't have a pair, so it's going to be stuck inside the radical. So that will give us 4 radical 3. So that's another way to do it, is to use a factor tree to generate what's called the prime factorization, and then match up the pairs and bring them outside the radical. Okay, so you can choose one problem at a time which method you want to do. If the numbers are small, you'll probably just use your multiplication facts. If you see a number that's really big, you might consider doing the factor tree. Alright, looking at number 2, again, as soon as I see that negative sign, I know that we are going to have I involved in here somewhere. So now I just need to worry about what is the square root of 18. This is small enough that I can definitely use my multiplication facts. 18 is 9 times 2. Always start with the perfect square. Square root of 9 is 3, so that means I have 3 radical 2. So that means I will have 3i radical 2. And that will be the answer to problem number 2. Okay, let's go back and take a look at problem number 3. Okay, again, I see that negative sign, so I know I'm going to have I involved. Alright, so now I'm just going to worry about the rest. I'm going to worry about 3 radical 50. 50 is small enough that I want to just use my multiplication facts. So 50 is 25 times 2. And I have this 3, I'm just going to bring that down. Now the square root of 25 is 5, just a regular 5. So I bring down the 3, this is multiplication, I bring down the radical 2, and 3 times 5 is 15. So this is going to be 15 radical 2. That means I have 15i root 2. That's the answer to problem number 3. Okay, let's take a look at problem number 4. 384 is a pretty big number, so I think I will use my factor tree method on this one. Again, I see the negative under the radical. As soon as I see that, I know I will have I involved. Alright, I'm just going to change colors. So, let's do the factor tree on 384. Now, I know that 4 is going to go evenly in because this ends in 4. So 384 will be 4 times something. So here I'm going to use a 4 function calculator to figure out what it is. Now obviously this is actually a scientific calculator. It's the only one I can show on the screen like this. But let's pretend it's a 4 function calculator because that's all you will be allowed to use. So 384 divided by 4. That's 96. Okay, so this is 4 times 96. 4, of course, is going to be 2 times 2. These are prime numbers. Okay, 96 is divisible by 3. Okay, that's 3 times 32 will be 96. And then 32 is 4 times 8. And then 4 is 2 times 2. These are prime numbers. And then 8 is 2 times 4. And then 4 is 2 times 2. Okay, wow, that is a lot of 2's. How many 2's do I have? Let's see, I've got 1, 2, 3, 4, 5, 6, 7 2's. So 384 is the same thing as, okay, 7 2's. So 2 times 2 times 2 times 2 times 2 times 2 times 2. And then we have an extra 3 in there. So that's times 3. Alright, every pair is going to become a 2 that's outside the radical. So that's going to be a 2. This pair of 2's will become a 2. This pair of 2's will become a 2. So these 3 2's are now outside the radical. Now inside the radical, I'm left with the 2 and the 3 that have no pair. I'll go ahead and make that into a 6. 2 times 2 times 2 is 8. So that gives me 8 radical 6. So that is what I get from doing the square root of 384. Now don't forget, we had this -2 out front. Okay, so maybe I'll change colors for a second. So we had this -2 sitting out in the very front. So really I've got all of this with a -2 sitting out front. Okay, so I've still got that -2 sitting out front. So really this is going to be -16 radical 6. So that's going to give me -16i radical 6. Okay, that's going to be the answer to number 4. Okay, take a look at number 5. 252. Again, this is a big enough number that I think I would like to use my factor tree method. Okay, so let's see. 252. Focus on that. This is definitely divisible by 2, so it'll definitely be 2 times something. Alright, 252 divided by 2 is 126, of course. So now I've got 126, this being a prime number. This will again be divisible by 2. Alright, this is going to be 2 times 63. 2 is a prime number. Now, 63 is going to be 9 times 7. And then 9 is going to be 3 times 3. And then all of these are prime numbers. 3, 3, and 7. That means the prime factorization is, it's going to be 2 times 2 times 3 times 3 times 7. That's the prime factorization for 252. Now don't forget, we have this 5 in the front. We might as well put that down right now. Now these pairs are going to become a number outside of the radical. So I'm going to go ahead and bring down the 5. That's obviously outside the radical. But 2 times 2 is 4. The square root of 4 is 2. So this pair of 2's will become a 2 outside the radical. Similarly, this pair of 3's will become a 3 outside the radical. This 7 does not have a pair, so it's going to be trapped inside the radical. Now, 5 times 2 is 10. 10 times 3 is 30. So that gives me 30 radical 7. Okay, because of this negative sign, I know I'm going to have an I. So that's why this is going to be 30i radical 7. Looking at problem number 6, I'm not going to need the factor tree for this because 125, all right, I'm looking at the square root of 125. I know that this is 25 times 5 because 5 quarters would make $1.25. So I've got 4 times this, see the 4 out here, so I've got the 4 times 25 times 5. The square root of 25 is 5. So that gives me 4 times 5 times the square root of 5. 4 times 5 is 20, so that's 20 radical 5. Because of the negative sign, I know that that will be an I. So I've got 20I radical 5 for problem number 6. Okay, what about number 7? Alright, so look, now we have some that have variables in them. So let's take a moment and talk about how variables work. If I want to do, say, the square root of x to the 6th power, that is going to be x to the 3rd power. So basically I just divide by 2. Okay, so if I had the square root of x to the 10th power, that would be x to the 5th power, for example. Now, what if it's an odd number? Okay, so what if I have the square root of x to the 11th power? I can't just divide by 2. So what I could do is I could split this up as the square root of x to the 10th power times an extra x. Alright, together this would make 11. So I just pull one of the x's off to the side. Now that leaves me able to take the square root of this first part. That would be x to the 5th power, because now I can divide by 2 again. But that's going to leave this x all alone under the radical. Okay, so looking at this particular assignment, I see a lot of 3's. Okay, so look at the way that this is going to go down. So I see the negative sign under the radical. I know that's going to be I. So I'm just going to ignore that for a moment. Okay, when I look at the 24, 24 is 4 times 6. Alright, 4 is a perfect square. So I've got 4 times 6. Okay, I'm putting the 4 in red because it is a perfect square. It will simplify and come outside of the radical. Now I've got x to the 3rd power. That is odd, so I'm going to split that apart as x squared times an extra x. X squared times x. Okay, and then y to the 3rd power, I'm going to do the same thing. I'm going to split that apart as y squared times an extra y. Alright, so this is the same as this, except for the negative will become I. Now everything I've shown here in red is going to simplify and come outside of the radical. Okay, so the square root of 4 is 2, the square root of x squared is x, and the square root of y squared is y. Now everything in blue is going to stay trapped under the radical. So I'm going to have 6xy left underneath the radical. So this is going to be my answer, except I will also have I. So I'm going to have 2xy I radical 6xy. Okay, and that's my answer for number 7. Similarly, looking at number 8, I see the 200. 200 is 100 times 2. 100 being a perfect square, so I'm going to write that in red, and then times 2, which I will write in blue. Now x to the 3rd power, I'm going to split that apart as x squared times the extra x. Okay, so everything in red is going to simplify and come outside of the radical. The square root of 100 is 10. The square root of x squared is x. Everything in blue is going to remain trapped under the radical. So that's the 2 and the x. So that's why my final answer will be 10x And I'll go ahead and put the I in there because of the negative. And then radical 2x. Alright, just for fun, I think I will use my factor tree method on 320. So here's 320. That 0 on the end means this can definitely be factored as 32 times 10. Now 32 is 4 times 8, and 10 is 2 times 5. These are prime. 4 is 2 times 2, prime. 8 is 2 times 4, and then 4 is 2 times 2. Okay, so for my prime factorization, what I have is let's see, I've got 1, 2, 3, 4, 5, 6 2's. So that's 2 times 2 times 2 times 2 times 2 times 2. 6 2's and a 5 times 5. Okay, and then I've got x, y, and z squared. Alright, that is what I have. Now, every pair of 2's is going to become a 2 outside of the radical. So this is going to become a 2, and this pair of 2's is going to give me a 2 outside the radical, and this pair of 2's is going to give me another 2 outside of the radical. Alright, that 5 is going to remain trapped inside the radical. So is the x, and so is the y. Now z squared is a perfect square. I can take the square root of that. The square root of z squared is z. Now this is going to look weird because z looks almost like a 2. So I'm going to very carefully put a line through it. So I have 2 times 2 times 2 times z. And then I'm going to have the stuff that's trapped underneath the radical, which is the 5, the x, and the y. So we'll have 5, x, and y. Now 2 times 2 times 2 is 8. So that's going to give me 8z, and then because of the negative, I'm going to have I, and then radical 5xy. So that will be the answer to number 9. Number 10 will be the last problem in this video. It's back to a nice easy number for some reason. Normally the harder problems are at the end, but not this time. The square root of 20. 20 is 4 times 5. So we're looking at 4 times 5. And then the square root of 4 is 2. And then, so that's going to be outside of the radical. And then the 5 is going to remain trapped inside of the radical. So because of the negative sign, that's going to be an I. So the final answer will be 2I radical 5. Alright, and that is how you simplify expressions involving imaginary numbers. I hope this was helpful, and I will see you on the next video, hopefully, where we will learn how to graph complex numbers in the complex plane.